So this will be our first video in this playlist where I'll be looking at some of the projects which I've worked on. Okay, so this project is titled cardio disease. I just saved this as cardio_disease. Okay, the first thing I did was to write up a brief introduction about the data set. I said CVD remains a leading cause of global morbidity and mortality, emphasizing the need for effective preventive strategies. In recent years, machine learning has emerged as a powerful tool in the healthcare domain, offering innovative approaches to predict and manage cardiovascular risks. Machine learning leverages advanced algorithms to analyze complex data sets, uncover patterns, and generate predictive models, thereby augmenting traditional risk assessment method. Then I talked about some of the key components of machine learning on cardiovascular disease prediction. The data which we'll be using is a very important key component. Then how to select our features which we would need from the data set, algorithm selection, how to train our model, risk stratification, early detection, and continuous learning. Okay, so I won't be reading this line by line. I'll be dropping the GitHub link to this particular project, so you can actually click on that link and view the projects and study it at your free time. Okay, so the next thing I talked about challenges and considerations. So what of the challenges I faced? Data quality. For your machine learning predictions to be accurate, you have to have a good quality data for training. So when there are biases in the data, such as underrepresentation of certain demographic groups, it can affect your model performance. Their interpretability also. So machine learning models, particularly complex ones like deep neural networks, are considered black boxes, making it challenging to interpret how they arrive at specific predictions. Then ethical and privacy concern. Healthcare data are usually patient information which needs to be kept private. So privacy, consent, and the responsible use of sensitive health data is another challenge when it comes to analyzing healthcare data. Okay, so the next thing was talked about the data and the methods which I use. So our data is a CSV file that contains the following columns: the patient's age, gender, occupation, sleep duration, BMI, and other rows of data. So I'll be reading in this data so that you can see what our data looks like. But before I do that, I looked at how to install and import libraries. So these are some of the libraries we'll be needing: Pandas, Datasys, MySQL.connector, NumPy, Seaborn for visualization of our data, Matplotlib.pyplot. So these are some of the library which I installed or imported. We'll be looking at other libraries as we go on. Okay, so the first thing I did was to connect to my SQL server because this data set was saved in MySQL. So I had to create a connection to MySQL using sql.connect and fill in my host title, user, password, database. That's the name of the data, it was saved in my database. Okay, so after creating that connection, the next thing I did was to read in that file as a data frame. Okay, because Python makes use of data frame. Okay, so I had to use pandas, that's pd I dot read underscore SQL underscore query to select all rows of that data from my SQL server and read it in as a data frame using pd.dataframe and data. We just saved all the rows SQL table as data, and now I'm reading in as a data frame. So I use the .head method to see the first 5 rows of this data frame, and you could see I said our columns contain ID, age, gender, height, weight, systolic pressure, diastolic value, cholesterol, glucose, smoke, if the patient is smoking or not. So you can see that this our data set needs cleaning. For example, look at our gender. We have 2 which is representing female, 1 which is representing male. If we want to do a visualization of this data set, we have to do some cleaning and change some of these figures. You can also see for smoking we have 0s and 1. So 0 is to represent that this patient doesn't smoke, 1 for a smoker. So we have to do something to clean up this value. CVD 01, 0 means this patient does not have cardiovascular disease, 1 the patient has cardiovascular disease. We have to clean this up. So that's the next thing I did, data cleaning. So the first thing I had to do was to check for missing values. There was no missing value. Okay, after checking for missing values, I did some cleaning of the data columns. Okay, like what I spoke on earlier, I had to replace 1 as male, 2 as female using the .replace method. Okay, I had to replace for smoking also 0 to be the patient doesn't smoke, 1 as yes the patient smokes. CVD also the column I replaced 0 to be no this patient does not have CVD, 1 the patient has CVD. The next thing is the age column. So if you look at this age column, you can see we have big values like 18,393. Definitely there's no age that is as high as this, so we have to change this to years, right? So the first thing I had to do was divide these values, which was the age values were in days, so I had to convert that to years. So how do I do that? Divide the days by 365, because 365 days make 1 year, right? So we have to divide that by 365 and ensure to round up those figure. Okay, so then I also had to drop the ID column because it wasn't useful. It's not a useful column, so I just had to drop that. Okay, so what other cleaning did I do? Systolic and diastolic column, there were some values that were too high or too low, like outliers. So I had to create a boundary for these values to ensure that some values were not greater than 200 for systolic, or neither was it lesser than 60 for the lowest systolic value. Same thing for diastolic. I ensured that the values were not greater than 180 or lesser than 50. So you can see I went about doing that in these lines of quotes that are here. Like I said earlier on, I'll be dropping the link to my Jupyter page where I have saved this notebook there, so you can go ahead and just copy and paste those codes, lines of codes, and it will work effectively. So the next thing I did was explore. Okay, before I talk about exploratory data analysis, you could see that if you look at our data frame now, after the cleaning, you can see it's now looking much more readable. You can see for age we now have 50 years, 55, 52 instead of those huge values we had. For gender, you could see we have female, male instead of 2 and 1 which we had. Then you can see our systolic values, our diastolic values are looking accurate. Smoking, you can see we have no and yes instead of 0s and 1. Same thing for CVD column also. Okay, so you can see data is looking much more cleaner now. So the next thing we did after cleaning our data set was exploratory data analysis. So first of all, randomly we just sampled 5 data points to see how our data looks like. aside from using the dot head, I just wanted to get a random pick of 5 rows of data and see how they look at. So I used the dot sample method to do that, and I also went ahead to look at the shape of my data set. I wanted to know how many rows and how many columns I had. So this data set contains 7,000 rows and 12 columns of data. So our size of our data set is 840,000. Okay, our size is just technically talking about number of rows multiplied by the columns of data you have, number of columns of data. So if you do 12 times 70,000, you see you get 840,000. So the next thing I checked was the types. What are the various data types we have in this data set? We have our age to be integer, gender to be strings or objects, height, weight. You could see that the columns that contains numeric values were integers, while those that contains strings were objects. I also use the dot describe method to do a brief description of our numerical columns. Okay, so you could see age. The mean age was 53 years, while the smallest age was 30. The highest or the maximum age was 75. You could also see that more than 50% of our data were from age 54 and above. The other 50 was from age 54 and below. Same thing for height, as our average height to be 164, our least or the smallest height to be 50, maximum to be 250. Same for weight, systolic pressure, and our diastolic blood pressure also. So using the dot describe method just gives you a brief analysis of a statistical description of your numeric columns. Okay, then another thing I also did was to use the dot describe tool for our categorical columns like gender, cholesterol, glucose, alcohol, physical activity, and all that. And for categorical columns, you could see that we couldn't get mean, marks, and all that, but we could get frequency, unique figures, and the top figures. Okay, so for gender, we could see that we have 2 unique figures, male and female, while the top most occurring was male. And we could also see the frequency, how many times this male value occurred was 45,530 out of the 70,000 rows of data we had. So for cholesterol, you could also see we have 3 unique figures. I think normal, low, very high, or normal, low, and high. And we could see that for normal, most people had normal cholesterol, and we had 52,385 of these rows of data having normal cholesterol. Same for glucose, smoke, alcohol, physical activity. So you can see all their data or information here. So you could see why Python is actually very useful. Just writing brief line of codes, you can get a whole lot of information from your data sets. So the next thing I did was data visualization. So with data visualization, I wanted to look at some columns, usually the categorical columns like gender, cholesterol, glucose, smoke, alcohol, physical activities, and CVD. So I wanted to see, we could just see some information here, but using visuals give us more perspective towards the information we have here. Okay, so first thing I wanted to do was for gender. I wanted to say, okay, with using this visualization now, I can now see that male is more than female. Here we actually got that information that the top and gender was male and had a frequency of 45,530, but using a graph to plot that information gives me much more insights to just that figure. I can now say, wow, there's actually a huge difference between male and female, because male is having 45,000 plus, while female we are just having 25,000 or so. Okay, So we can see that this data set is not proportional. The amount of patients which are male is times 2 of that of the female. Okay, so for cholesterol we have normal, very high, and high, and we can also see that many of our patients has normal cholesterol values. So for glucose we also have normal, high, very high. We can also see our glucose values, and more of our patients has normal glucose values. Same thing for smoking. Most of them say they don't smoke. Alcohol, most of them don't drink alcohol. So you can see that just really are just few numbers of people that take alcohol. For physical activity also, you can see most of them carry out physical activity, right? For CVD also, we can see now that the people that have CVD and those that don't have CVD are most likely same. So although we have huge difference in physical activity, smoking, whether a patient takes alcohol or not, you can see that both those that take alcohol and those that don't take alcohol, there's likely an equality in values between people that have CVD. Okay, and using just this brief line of code, I was able to, using just this should I say 6 or 7 line of code, I was just able to plot this graph, plot all this graph we just looked through. Okay, so you can see how Python is very efficient. So the next thing I wanted to do was, aside from that, I wanted to get more information. So I want to relate this to CVD, because we've seen people that smoke, people that don't smoke, people that drink, people that don't drink, and we could see that there was huge disparity between these two people, those that smoke, those that don't smoke, those that engage in physical activities, those that don't engage in physical activities. But when we looked at CVD, which is what we want to predict, we could see that there was no much difference between the values of people that have CVD and those that don't have CVD. So we want to see what's actually going on in our data set. So I wrote another line of code to be able to gather more information, to be able to understand how these various columns of data relate with people that have CVD or those that do not have CVD. So for gender, I created a graph that I could see for female, male, saying yellow box to show those that have CVD, and the blue box to show those that don't have CVD. Okay, so we can see that there's also an equality between those that have CVD and those that don't have CVD, even across gender. Okay, so you can see for male gender, which male are more, we can see that those that have CVD and those that don't have CVD, the difference are not much. They are almost same thing, even for female also. Then for cholesterol, you can begin to see some differences, some slight differences. Now you can see that although for those that their cholesterol values are normal, we could see that the people that don't have CVD are a bit more than those that have CVD, and for those that their cholesterol values are very high, we can see that they contain more people having cardiovascular disease. Same thing for those that their cholesterol values are high. Then if you go to glucose also, you can see that for those that their glucose values are normal, there is just little slight difference between people that have cardiovascular disease and people that do not have. Same thing for high and very high. So I just wanted to see this information to be able to get more understanding of the data. So you can see for smoking, there's not much difference between who has CVD and who does not have CVD. Alcohol, you can see same thing. Physical activity, just slight difference. Okay, so the next thing I want to do now is feature engineering. So we've looked at our data sets now, so now I want to do feature engineering to be able to get that information to what are the best columns we can use, for our machine learning. So feature engineering is the process of using domain knowledge to select and transform features from raw data before building a predictive model using machine learning. So we want to select the best features that we can use for our machine learning. Okay, so these are the features of data: age, gender, height, weight, systolic, diastolic, cholesterol, glucose. Now these are columns of data, and what are we predicting? Our CVD. So these are columns of data. So what I did first was to pre-process these columns of data. So these, we have age, our height, weight, systolic, diastolic. For gender we have male and female. Now we have our male to be 0, female 1, cholesterol normal, so yes, no. Okay, for cholesterol we have normal, high, and very high. So we have those values, 0s and 1, representing each values. And we use how were we able to do this? We use the .get dummies method, and we use drop facts to be equals to true. Okay, so same thing for glucose normal, glucose very high, smoking, and hold. So you can see our features have been pre-processed using the .get dummies method. So next thing, I just wanted to see our types, our data types. So now they are all integers. Another thing, next thing I did was to look at the correlation to avoid overfitting of the model. Okay, so if two values are too correlated, we have to drop down that column to avoid overfitting. So how do I do that? I use the .call function to check for correlation, and I sorted those values, relating it to if a patient had CVD as CX. Okay, so does the patient have CVD? Yes. So I want to see how correlated those columns of data is with a patient having CVD. So you could see systolic correlating with a patient has CVD was 0.4, diastolic 0.2, age, and so on. Okay, correlation is between 0s and 1, with 1 being perfectly correlated and 0 being non-correlated. So, and we also have minus and plus, where plus is positively correlated and minus is negatively correlated. Okay, so you can see how each column is correlated to if CVD is yes. So the next thing I did was to create an heat map. This information which we are seeing here, I had to create an heat map to be able to visualize it and see it much more better. With heat map, it uses color grading, so you could see for ones which are perfectly correlated was in this lighter color, while values which are not correlated becomes darker with time. So you can see black, you can see this negatively uncorrelated, you could see 0.2 a bit correlated. So the darker the color, those columns are not correlated, while the lighter the color, the columns are correlated. So you could see there's already a scale here for you to access that information. So the next thing I went ahead to do after getting that information was modeling. So before I talk about modeling, after assessing this information, there was actually no column that was perfectly correlated for me to drop. If there was any column aside from this CVD, yes, that is one. If there's any other column, let me say if systolic was 1 correlated with yes, CVD, yes, that's perfectly correlated, I would have to drop systolic, because it's going to cause overfitting of the model and affect our predictions. Okay, so but since there was none, I didn't drop any column. So for the modeling now, since we want to predict if a patient has cardiovascular disease or not, I had to drop CVD underscore yes, because this is the column I would be predicting, right? So I had to drop that. So that would be our y. For our x values, other columns which we'll be using are going to be our x values. So that's why you see I had to drop CVD from our columns which we'll be using. The next thing I did was to check the shape of our data. So now we have 70,000 rows of data still with 13 columns. So the next was to check if the data is balanced. So you could see cardio underscore data CVD yes, and use dot value count. I want to get number of rows of data that were yes, that had CVD, and those that were no, that didn't have CVD. So you could see 0 for no was 35,000. So 35,000 rows did not have CVD, while 34,000 plus rows had CVD. So you could see that the data is a bit balanced, right? So when I mean a bit balance, is one value is not way more than the other. So in case, for example, if we had 50,000 plus or 70,000 plus of rows of data having CVD, while 35,000 are not having CVD, you will know that that data is not balanced. You are not going to get true values when you do your predictions. So the next thing was to import and install those libraries I'll be using for modeling. So I had to import LGBM classifier from LightGBM, then also import train, test and split method from Scikit-learn model underscore selection, also precision score, record score, accuracy score, because these are what I'll be using to check the accuracy, the precision score and the record score after each modeling, right? So the next thing was to use the train and test to split features and the target variable. So what's our target variable? CVD underscore yes. What is our features? Those are the columns which we'll be using, like age, diastolic, systolic, and all that, right? So using the train underscore test underscore split, you take in your x. We've already done that. We've already set our s variable to be our features when we went ahead to drop CVD underscore yes column from our cardio data, right? And we also created a y variable when we did this by setting CVD underscore yes dot values to y. Remember, we are using the dot values because modeling takes in arrays of data. So we'll pass in our x, which is our features, our y, which is our target variables, test size to determine how we want our data to be splitted as train and test. So we want 70-30, that's 0.3. So we want 30% to be our test size and the 70% to be our train data. So stratify to be equals to y, and our random state, set our random state to 23, meaning we want those rows of data to be randomly selected or picked. The next thing I did was to define the model. Okay, so this first model was LGBM classifier, so which I've already imported. So LGBM classifier, so to define the model is just so had this open bracket and close bracket, and save this as a variable because we've already defined this model now. So this is what we'll be using, our LGB model. Now we're going to fit this model to our train and our y train features and targets. Okay, so S train, y train. So you can go ahead and number of positives. So if you go ahead and run this, you get this information. Number of positive to be 24,485, number of negative as this, and it just give you a whole lot of information which you just can go ahead and read. Another thing we did was, okay, so now go ahead and predict, because we just fitted our model to our training data set. So now let's predict on our test data set. So we use the dot predict method to predict on our hex text and our hex train also. To check model accuracy, precision and recall score, you can now go ahead and use those accuracy score which you have also imported earlier on. Remember we did this, we imported precision score, recall score and accuracy score, and those are the metrics we'll be using to check how accurate our predictions are, right? So I went ahead to use that using accuracy score, call our Y train and our train predictions. Okay, so we want to check how accurate these values are. You can see for our training accuracy score we got an accuracy of 0.75, that's 75% accuracy. Then same thing, we also check our precision score. On our precision, how precise was our prediction? We also got a 75% precision. And for recall, we got a 69% as our recall score. Okay, so that's for using the LGBM classifier. After that, I also went ahead to visualize what are the top features that was used for these predictions. Features, remember our columns which we use for prediction, those are the top features. So I went ahead, to get importance. How do you do that? LGB model, which you use feature underscore importances underscore. So you can just go ahead and pd.data frame your feature importance, or your feature names is the names of those columns which you use as your features, right? Then your importance, which you've gotten from feature underscore importances. So you can also just use the sort values so that it will give you an arranged graph just like this. So you can see that for this model, LGBM model, the most important column or the most important feature was weight, that was used for predicting if a patient had CVD or not. So the most important was weight, followed by age, height, systolic, then diastolic. So that's the most important feature used. Then after doing this, I created a Pico file because I wanted to use this to, or I actually used this to create an application which will be used to predict if a patient has CVD or not. So after visualizing the top features, I created a Pico file. So to do that, you just import Pico. Then to create the file, now you have to create file as a variable, open your brackets and place in your model. Remember, LGBM model was what we used for our prediction .pico because we want to convert this to a Pico file, right? Then write binary WB. So we just have to dump this as a Pico file and close, because this is the model we'll be using when we want to create our application, right? So this was how I created the Pico file. In the next video, I'll be showing you the codes I wrote to be able to create the application or an app which would be used in predicting if a patient has CVD or not. So in our next video, I will show you how I went about doing that. So this is just the lines of code I wrote to this point of creating the Pico file. So this all it is. Okay, so like I have said, within this class I'll drop the link to the GitHub page that contains this notebook, so you can just go ahead to the GitHub page, download this notebook, and you can use it to practice at your own convenience also. Okay, I hope you actually enjoyed this class. I hope I wasn't too fast or too slow. I promise to do better in the next class or next video. Please remember to subscribe, share to your loved ones, your family that are interested in coding. Okay, and see you in the next class. Bye.